Third presentation is a paper called Ambient Occlusion Using Bone Tracing with Scene Voxelization. It's going to be given by Eduardo Favera, and he has just finished his PhD, master's at PUC-Rio with Valdemar, now working at CEGRAPI.
Hi, I am Eduardo, and I will present ambient occlusion using cone tracing with scene voxelization. A brief summary of the presentation. First, I will introduce the concepts of ambient occlusion, present some related work, clarify our method, present our results, and finally conclude and present future work. Well, in computer graphics, we are always seeking for realism, and one way to achieve this with the correct modeling of the light and how it interacts with all the objects of the scene. And way to do this is global illumination. The problem of global illumination, it cannot be rendered in real time. But some techniques that compose the concept of global illumination could be dismembered and used in real time. One example is ambient occlusion, which can give the global aspect of a scene with low computational cost. The idea of the ambient illumination is that the light that comes to a scene reflects on every object and is used to light all other objects. The result is an effect, a light that comes from all directions. The equation of the ambient occlusion could be seen like this: a sum of all directions of the hemisphere of a point, and for each direction you solve the visibility function V and weight its results by the dot product of this direction with the norm of the point. In here, you can see a little example in this picture. The point P, all the dashed rays didn't hit any geometry, so they will not account for the ambient occlusion of this point. So we just sum the other points, okay? So our proposal here is a novel algorithm to efficiently generate high-quality results in ambient occlusion. To do that, we evaluate the ambient occlusion only for the visible pixels, and we also use a regular grid to assess the geometry information, not the total triangle mesh. And we use cone tracing, the technique of cone tracing, to calculate the ambient occlusion. The technique of cone tracing is basically, instead of tracing lots of rays, we use a cone to simplify the calculations, okay? Some related work. There are several ways to resolve ambient occlusion. The direct translation of the ambient occlusion equation is to use ray tracing, which gives us very good results, but the performance is low. The way to the loss of applications used to have real time is using screen space methods that use only the information in the scene, the screen buffers, to calculate ambient occlusion. But however, the ambient occlusion is a global effect, and not always only the information in the depth and the screen buffers are enough. So they have good performance, but sometimes they can have some errors. The volume space methods, they use the volume to calculate the ambient occlusion. So it have much more information than screen space methods, and they have enough performance to be used in real time. Our method fits in this kind of methods. Some related works. A screen space method presented by Zirma and Carlos tries to resolve ambient occlusion by replacing the direction trigger integral of ambient occlusion by a volumetric one. He does that by obtaining the volume of a sphere tangent to the point P. In this picture, we have point P, and the this semicircle is the influence of this point. So he calculates the volume of this sphere tangent to the point P. He calculates the occluded volume of this sphere, so he can have the occlusion of this point. To calculate the volume of this sphere, tangent sphere, he does a cylinder sum, and the height of each cylinder is bounded by the depth buffer. Okay, that's how he uses only the information in the screen to calculate the dimension occlusion. The volume space methods usually represent the scene using only voxels. Okay, so there are several ways to voxelize the scene, and one algorithm that's very interesting was proposed by Eisenman and Decorah, and he proposed a single path voxelization algorithm. So at every frame he builds a binary solid regular grid. It's a regular grid with only two states at each voxel. It can be a full voxel or an empty voxel. And he also produced results that are solid. So you can see the bunny here, it's cut. This is hollow in the inside, and this is full. So all the voxels inside the object are full. He used the rasterization hardware and bit operations to construct this grid, and the result is a 2D texture with the grid. Okay, so if you fetch a text of this RGBA texture, each bit of this texture is a voxel. So if it's 1, it's full; it's 0, it's empty. The restriction of this algorithm, it only accepts watertight models. One work that uses this algorithm is from Papayanoa and Autry, and he proposed to use Hay-Martin for each visible pixel. So he has the volume, and he iterates rays at constant steps in the volume. So if any ray hits the geometry, he returns 1 and stop. If the ray is out of influence radius of the point P, he returns 0 and stop. So we count all the contributions of all rays, and we have the ambient occlusion. Another method that are related to ours was proposed by Krassin and Autry, and he used a dynamic voxel tree, so he doesn't use the algorithm of Eisenman. He proposed to divide the hemisphere of a point in several cones and perform cone tracing in each one of these cones. He does that by along the axis of the cone, he fetches the octree at different levels. So with this, you have the information of occlusion in the cone. Our method can be divided in 3 steps. First, we only want to estimate ambient occlusion for the visible pixels. We do that using the deferred shading. So we construct 2 G buffers, first with normal and then with depth. The next step, we compute the regular grid for each frame using the algorithm by Eisenman. So we have the triangle meshes. We will then have the voxel grid, and then we resolve ambient occlusion using our method of cone tracing. Our method of cone tracing, just like what the method proposed by Krassin, divide the hemisphere of the point in several cones, and each cone is divided in spheres with crescent radii. Then we use each sphere to sample the regular grid. To sample the regular grid of each sphere, we distribute several samples around a disk, inside the disk, in the center of the sphere, and each sample defines a prism, and this prism is parallel to the z-axis of the grid. So the advantage of this is only one axis we can get all the voxels in the z direction of the grid. So we have to remove all the bits that are out of the sphere. So we remove these using binary operations, and we count the full voxels only in this range of the sphere. as we do that for all the samples of the sphere, we can sum, just like the method proposed by Sirma and Carlos, and we'll have the occluded volume of this sphere. After that, we attenuate the resulting occluded volume by the distance the sphere to the cone apex. We do that because spheres closer to the point tends to occlude the light. So we give more weight to this sphere. After that, we have to accumulate the results of all spheres to the cone. We explain this with an example. Here we have a cone composed by 3 spheres, and each sphere has its occluded volume calculated. The first has 30% of occlusion, second 25%, and 65%. As the cone represents a bunch of rays being traced, at this point, before the first sphere, we have 100% of the rays. After the first sphere, 30% of the rays were blocked. So we have 70. From the 70% of rays, 25 were blocked. So we have 52. And in the end of the cone, we have 18% of the original rays being traced, which is 81% of occlusion in this cone. After we do that, we sum all the cones and normalize the result by the number of cones, having the final occlusion for this point. Some results, just limitations, C++, use OpenGL, shading language, GLSL. To test our result, we propose 3 quality settings with varying trade-offs between quality and performance. This is the attributes that we vary for each of the quality settings, and we can see here that the number of cones was fixed. We choose to fix it because it was good enough for all the quality settings. We compare our results with the ray tracer from NVIDIA Optics. It's made in CUDA, it's not real time. So it's our quality reference. Here are some results, just the Buddha model with each one of the quality setting and the reference. You can see that the results tend to get closer, but are good enough even in the lower quality configuration. And the performance tends to decay as we use higher configurations, quality configurations. This is another model, carburetor model, same conclusions as before. So our results tend to get close to the reference, but something that we notice with some of our results is that some regions, some small cavities in the reference are very dark, but in our algorithm, they are not dark enough. And they should be dark. There is a lot of geometry here, so it should be well occluded. We believe that the problem here is in the resolution of the grid in the Z direction. It's not enough. In a 2D texture with 32 bits, we only have 128 voxels. So we think it's not enough in this direction to correctly voxelize this scene. Okay? So this is a problem of our algorithm. But our results show that our medium quality setting was good enough, and we use in the next test. So this is medium quality setting. We compare with the application from NVIDIA, which was using screen space to calculate ambient occlusion. So we have NVIDIA screen space, our method, and the reference. As you can see in the frames per second, the screen space method is quicker, but it's expected. It only uses the information in the screen. However, you can see in these details that in that region, in the screen space, there are some errors. Should be occlusion in there. The occlusion is not correctly calculated because the occluded region, the occlusor region, is not visible by the viewer, so it not correctly occlude that region. And our algorithm is very close to the reference. Okay. is a video with some of our models. Okay, this is real time. Only with ambient occlusion is the carburetor model. It's another one model. So this is using medium quality setting, and we have a dynamic model here, animated. First, only ambient occlusion. You can see it's fully dynamic. We will turn on the light so we can compare the gain in quality with diffuse illumination. Just to enhance this, we turn off ambient occlusion, and we will turn on again. So you can see the gain in the 3D scene using ambient occlusion. Okay. Some of our conclusions. So we proposed a method to estimate ambient occlusion in real time. To do that, we divide the hemisphere in cones. We divide each cone in spheres, and we proposed a very efficient method to sample the geometry using spheres. So I think this is our great contribution. Our results show that we are very close to the reference, and we have good performance even compared to screen space methods. And we can say that our results can be improved even more if we use more samples. Okay. As future work, to study the use of this algorithm in static scenes, so the voxelizing in pre-processing stage. So, and employ this method in scientific visualization. This is a black oil reservoir, and we would like to see if the use of this technique can enhance the analysis of the data. And we have a little bonus section, something that we are still working on. It's not in the paper. We are trying to solve the issue of the low grid resolution DC direction. And so we think we could construct the grid only for a portion of the Z distance. So we will not voxelize the full frustum. So the idea is that we improve the resolution of the grid in the region near to the observers, which is the more important. But this can cause errors, as regions that are farther from the observer maybe will not be correctly voxelizing, and maybe it will affect the occlusion of all of other objects. And these are some of results so far. That on the top, on the left, our original method with the cavity that it's light, it's not very dark, the reference, how it should be, and how we got so far. So it's darker. The scene changed a little bit, but it's still very close to reference, and we are getting better results as we work in this one. Thank you.
Now we have time for questions. So let me try something here. So you said that your future work is to apply this for a scientific visualization or something like that.
Yes.
And there the issue of the resolution will be more dramatic. So you have any thoughts on how you're going to handle like a big scenes? Because the ones that you showed here are small geometric models, right?
Yes, we are not studied the use in big scenes yet, but we think that a big scene with only one object like this reservoir tends to the picture in the front. We will occlude the regions farther. So who is analyzing the data? We need to see the region that's closer, and that region will have higher resolution and will be correct. Other things that it probably enhance the quality of the analysis, but it's not something that will affect the global analysis. So it's just illumination. So probably once, if there is some errors in the back, it will not be a big problem.
Okay, thank you. Any more questions? Okay, so let's thank Eduardo again.